Hello guys and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're tackling a problem on internal forced convection, that is convection that's happening not because of the difference in densities of the fluid, but because there's an external force, external flow, a velocity, external velocity, pushing the molecules with higher energy away. In this case, it's internal because it's occurring inside a pipe. Problem statement reads, air flows through a 1 meter long, 80 millimeter diameter tube at a rate of 1 kilogram per minute. Measurements indicate that the average wall temperature is 150 degrees Celsius and flow is fully developed. The air enters the tube at 40 degrees Celsius. Estimate the heat transfer rate from the tube wall to the air. So we are after the heat transfer rate, which we've been calling uppercase Q with the dot to indicate it's a rate, right? And so that means we're looking for a figure in the units of watts. All right, so let's start by drawing the problem simply. Drawing the pipe or the tube that is mentioned in the problem. It has a diameter of 80 millimeters, or 80 times 10 to the minus 2 meters. We also know up to minus 3 meters. We also know that the length of this guy is 1 meter. What else do we know? We know that we have air, and I always encourage you guys to write down what you actually have so you actually look at the right table, because believe me, it's not uncommon for people to grab wrong properties at the wrong table because they simply are too used to using one type of flow. And this guy, this air is coming at 1 kilograms per minute, not per second, per minute. Per minute. Cool. We know that the wall is at 150, so T wall or TS is 150 degrees Celsius, and that the temperature of the air on the inlet, so on the inlet is 40 degrees Celsius. So we know beforehand that our Q, the one we're looking for, is going to be flowing from the wall into the air, correct? And we also know that this air will be heating up, right? So that means that it's entering at 40, so it's 40 over here, but it's going to leave at a temperature T2, which is higher than the 40, correct? So therefore, what we do is, okay, we don't know what's the outlet temperature as of yet. So what we can do is grab the bulk temperature, that is the mean temperature between this guy and this guy, and with that we can find properties that are theoretically closer to what we're actually having in our situation, right? So something that's closer to the bulk temperature of the air inside this tube. Now, when we do that, mind you that you're doing a assumption, right? The assumption is that your T bulk is somewhere close to 40 plus 150 divided by 2, which gives us 95, and that's in degrees Celsius, which is the same thing as 388, and that is in Kelvin. Okay, and mind you that this is an assumption. So if we calculate our variables and we find out at some point we're going to find out what is the heat coming out of this, that allows us to actually calculate, because we know the specific heat of air, that allows us to calculate what is the temperature that is leaving on the other side. Yeah? And then when we do that, we can see whether it's leaving, maybe it's leaving at 60 Celsius. And if that's the case, then we probably want to do it again, right? Because our bulk temperature is going to be actually closer to 50 than 95, right? So you don't need to do that for every single problem, but as a rule of thumb, remember that what we just did here is an assumption based on the information we have at the start, right? Which is different from other problems in which we, for instance, have the temperature at which air is entering and the temperature at which air is leaving, for instance. If we have that, then our bulk temperature assumption is way, spot on, or as close as can be. But it's not the case in this problem. Okay, so game plan. What do we want to do? Well, we want to find what is, whether this guy is turbulent or laminar, and we also want to know if it's fully developed or underdeveloped, right? The problem statement in the beginning already says quite clearly that this guy is fully developed, so that's one down, right? So this means, okay, we have this situation here, this guy goes out. So all we need to find out is whether it's turbulent or laminar, and once we do that, then we can find out what is the correct correlation to use in this problem. And then with that, then we can find out what is Nusselt. With Nusselt, we find the convective coefficient. With convective coefficient, we find the heat transfer, right? So what's the idea here? Find out Reynolds. With Reynolds, I determine whether it's turbulent or actually before, right? Properties, because I need properties to be able to solve for Reynolds. Then I'll do Reynolds. Then that's going to allow me to determine whether it's turbulent or laminar. Then I can find the correct correlation, which allows me to find the Nusselt. Then convective coefficient, which then finally allows me to apply Newton's law of cooling and solve for Q. All right, so properties first. So air properties, we're looking for 388. Air properties at 1 atmosphere. So 388 will be somewhere between my 350 and my 400. Again, several ways to do it. You're going to have to do a linear interpolation. This video shows you what linear interpolation is if you are new here. If not, you guys already know that what I generally do is just this, just to show where things are coming from. 400. And what are we after? Well, if we need Reynolds, we want to find out what is the viscosity. If I'm also going to find Nusselt, and then I'll need the the conductivity to be able to find the coefficient, and I'm also grabbing Reynold for the same reason, right? So viscosity and Reynold and the conductivity, and we're doing that for 388, which is what I'm looking for. So at this point in time, just writing down the values that I do have. So this is a specific heat. I'm looking for the dynamic viscosity. So that's just 2.075, and this is 2.286. These are both times 10 to the minus 5. Prandtl is 0.697 and 0.689, and my conductivity is 0.033.03365, and then now I can do the interpolation. If you already know what the interpolation is, but you want a faster way of doing it, I'll share another video that tells you, different ways of doing it. If you want to do it by hand, if you want to do it using a calculator, or if you want to use a spreadsheet like Excel or Google Sheets, you can use the video there to help you out. And this is the result of our interpolation, 0.03278. Okay, so these are the properties at 388, assuming a linear interpolation. Okay, now Reynolds. We know our Reynolds is the density, the free stream velocity, the dynamic viscosity, and my characteristic length, which in the case of a tube or a pipe is the diameter, right? Now note that we don't have this guy here, and this has happened in previous problems. And then we talked about how the free stream velocity, if I multiply the free stream velocity times the cross-sectional area, that is the area perpendicular to that velocity, that is equivalent to my mass flow rate in my specific volume, right? So that means that I can, where I have the free stream velocity, I can simply substitute that by the mass flow rate, specific volume, and cross-sectional area. This guy, pi r squared, or pi d squared over 4, specific volume. This is the inverse of the density, so we could write this as this if I wanted to. And I'm just substituting that in, and what happens is we end up with another way of calculating Reynolds, which is just 4 times the mass flow rate divided by the dynamic viscosity, pi, and the diameter. I did this before, so I'm not going to spend a lot of time here. So 4 times my mass flow rate. Mass flow rate is 1 kilograms per minute. So I want to be sure that I want to have that for a second. So just that thing we always do without rushing. We know that 1 minute is exactly the same thing as 60 seconds. So therefore, if I'm multiplying by the parentheses here, I'm multiplying by 1, I'm not changing anything. But in terms of the units, what I do end up with is kilograms per second, which is what I'm looking for. So just 1 over 60. So I'm just going to put that as 1 over 60 here. And then I'm dividing by the dynamic viscosity that we just found doing the interpolation. So 235 times 10 to the minus 5, pi, which is pi, and the diameter in meters, which is 80 times 10 to minus 3, to have my Reynolds without any dimension. And this gave me 11,868.37 .3775. So I'm just going to leave it at this, okay? Just at this for my Reynolds. And this Reynolds is greater than the 10,000, right? So greater than 10,000. 1, 2, 3. So therefore, this is a turbulent flow. And that is the information that I was looking for to be able to find the correct correlation. right? So I have a case in which my flow is turbulent plus fully developed. And this now I need to find a correlation for this kind of situation. Now, we've talked about that before. Let me see if my correlations are here anywhere. Put them here. If not, let me just pause the video and get the correlations here. Okay, so this is somewhat a simplified view of the possible correlations we have. This is a situation in which we have turbulent flow and fluid developed, which is exactly our case. And then we just need to figure out what is this N here. And this is if the fluid is heating up, we use that one. If it's cooling down, we use the bottom one. Other options, if it's laminar and fully developed, then there are two options of constant Nusselt, which simplifies our life by a lot. And if it's turbulent and undeveloped, there's yet another correlation here for us to use. Okay, so our case is absolutely this one, first one. We want to apply this guy here, and our fluid is receiving energy from the wall, right? So therefore, we know this is our case here. So it's going to be this correlation with the N of 0.4 over here. Okay. So if I'm looking for my Nusselt, this is going to be 0.023, my Reynolds to the 4/5 or 0.8, my Reynold to the N, and that's 0.4. That's per what we saw. We have everything we need. Let's just plug it in and be happy about it. It's 11868 to the 4/5. Parental is 0.691. This is to 0.4. And this relationship gave me a Nusselt of 3606. Okay? And we know that this guy has to be equal to convective coefficient divided by my conductivity and the characteristic length. In this case, it's a tube, so it's the diameter. Okay, so that means that if I want to find what is the convective coefficient for my situation, I'll multiply my Nusselt, 306, by my diameter, which is, sorry, by my conductivity, which is the 0.3, where is it? 0.0327, 0.0327.8, and I'm dividing the whole thing by the diameter, which is my 80 times 10 to the minus 3 to make sure our units end up as watts per meter squared per Kelvin. And this gave me 1477. Yeah, and just, it's probably good practice to just ensure we have the right units. Nusselt number doesn't have any units, and then we have the conductivity, watts per meters per difference in temperature. And then down here, because my diameter is in meters, I have meters again, right? So watch out. If this is millimeters, you're going to have millimeters times meters, you're going to have a problem there. So indeed, all our units check out, all good. And now we can go to find out what we're looking for from the start, which is heat flow, Newton's law of cooling, H, A, delta T. We knew this from the start. That's going to be, our difference in temperature times our bulk temperature, the one that we assumed in the beginning. The area, that's the area through which heat is being transferred between the pipe and the air. So it's going to be the surface area of the cylinder. And then this is the guy we just found, right? So this is equal to 14.77 area, 2 pi r L, or because 2r is the same thing as diameter, pi dl. And then delta t, my 150 minus my 95, which remember was the assumption. Okay, so Q, I should have put that over there. So this is my 80 times 10 to the minus 3. This is 1 meters, 1, and everything else is all good. So this turns out to be, what did I get? About 400, oops, not 95, or 95 or 40. Should be 95 here. That's the bulk temperature that we're assuming for our here. So if that's 95, then this fella becomes if we're assuming this guy to be 40, that is, if we're taking just the inlet temperature of the air, the only air temperature we do know, then This turns out to be about 408.5. Note the difference there. Completely depends on the assumption, right? Now, what we can do, as you know, this is the problem, but what we can do is we can now go back and check. Okay, so we know the heat capacity of this guy is this fellow here, so we can interpolate that. We don't really need to interpolate much because the difference between the two is not, for the sake of what we're trying to find out, it's not going to be that different. So we can probably go with you know, a value of 400, which is closer to the 388. So 1.01, that's good enough. That is in kilojoules per kilograms per Kelvin. And then the following situation occurs. The Q, right, the rate of heat times the mass flow rate times the heat capacity is going to give me the delta T of the air. Now, if it is, and we can do both now here, it's probably what we want to do. If it's 65, it's going to be 65 equals 1 over 60, which is the mass in seconds, times the 0.11 times 10 to the third to have it in joules instead of kilojoules. And then over here, I'm going to have my temperature of the exit, it's my known, minus the 40, which is my known temperature. And over here, I'm going to have exactly the same thing, except instead of 65, I'm going to be using my 408. All right, brilliant. So that means that if I'm doing the assumption of my bulk temperature at 95, this means that my outlet temperature would be 43. Okay, so entering at 40, leaving at 43. So this means that I would probably want to go back, redo this with the properties at 40 Celsius, or excuse me, at 41.5, right? Which would be the bulk temperature there between the 40 and the 43. And if not, if we're doing this one here, then my new bulk temperature is going to be about 100, about, what is it, 50, right? So 60 plus 40 divided by 2, it's about 50, and then I can do the properties at 50. It's interesting to go back and see how the properties are going to change, right? We know that, so we know that the assumption of 95, it's probably too high, because if my bulk temperature is 95, I'm assuming that my air is leaving at about 150, correct? And clearly that's not the case. So therefore, my outlet temperature is probably going to be somewhere closer to the 64. Yeah. So this is where we go back and now get the properties at let's do 50 Celsius, which implies that my outlet temperature is 60 and my inlet temperature is 40. So we have to do the whole dance again, right? So we need to grab the properties, interpolation, everything. We need to make sure that this is in Kelvin. So we're looking at 323 Kelvin. So that means that when I'm interpolating now, I'm going to be interpolating between 300 and 350, as opposed to the 350 and the 400. And I'm going to be grabbing, again, Reynold, conductivity, and dynamic viscosity, and I'm looking for 323. Notice quite close to the center. So if you're in a hurry or in an exam, something like that, what you can do is just take sum of the two of them up, divide by 2. But if you do the proper interpolation, you get 1951 17 minus 5. Here you get 0.703 approximately, and here you get 0.02798. Okay, so we're redoing all our steps, except this time we are using different properties. So what do we need to redo? We need to redo this part here, and this part here. I have copy more than I need. Let's see. Okay, so here, this is the same mass flow rate, same diameter. What changes is this guy. So this is 1.951, which gives me approximately 13,596.01427. So let's just go and keep it at 13 596. Good enough for me. That's all still turbulent, so nothing changes in that regard. Still fully developed in turbulence. Let me just make sure this is better. So then this guy needs to change. Let me leave this in red. So this is going to be now 13,596. This guy is going to change too because now this is 0.7. What did we find? 03. Then that means that this value changes, and this becomes, I got 40.47988. So let's go ahead and approximate that to 40.5. This has to be equal to, again, same thing, does not change. Now, this value is different. This is now 2798. And this value is now different. This is the 40.5 we just found, which means this value is now different. Not very much difference. This is 1477. What we get out of this is 1415. Okay, so not that much of a difference. What will change, right? The real difference is when we go to calculating Newton's law of cooling, calculating Q. This guy here is a real change, right? This is the real big difference. So this now became 1415. This is the same, and this is the same T-wall, right? But now the difference here is my 50 Celsius, right? So this is my new bulk temperature, because I know my hot air is going to be leaving, or I assume my hot air is going to be leaving somewhere close to 60 Celsius. So therefore the bulk temperature, more realistic bulk temperature, is 50 as opposed to the 95, which was our original one, or the 40, which is the entrance temperature of the entrance of the air, right? And this gives us 355.8 something. So let's just go ahead and once again and approximate this to 356 watts. All right, so this is, at this point now we can be comfortable and say, okay, this is my final answer. All right. So obviously at the start, on the very start, when I started solving this, you have some options, right? This is the assumption that I made, bulky assumption, I guess, a bold assumption, I should say. You could have, assumed, oh, you know what? I'm going to go ahead and assume the bulk temperature is 50, or I'm going to assume the bulk temperature is 60, or I'm going to assume the bulk temperature is actually 40, right? The problem with 40 is that then you're going to have to, if you do 40, then, I think that's where your error is increased by a bigger margin, because you know that the air is going to be receiving energy from the wall from the get-go. So when it leaves, even if it doesn't get much energy, its temperature is going to be greater than 40. Right? So if you say your bulk temperature is 40, what you're telling me is that it's leaving at, leaving at 40.5 or something. And that's you're probably going to be pushing it if you do that. So, depending on what you do initially here, then you might need to do a couple more times like I did just now. Depending on if you were to guess, about 50 or 60, you probably wouldn't have to go back and do it all over again. All right, so I hope this helped you out. I hope this made sense. If not, if you have any questions, just leave them down below as per usual. If it did help you out, consider liking the video, and we'll talk soon.